we're going to move on to our next speaker from Honeybee Robotics, who work on the next generation advanced robotic and spacecraft systems that must operate in dynamic, unstructured, and often hostile environments such as drilling, sampling, and exploration tools for both planetary and terrestrial mining and exploration. And we're hoping this has to do with drilling on Mars. Please welcome Kris Zacny, Vice President and Director of Exploration Technology for Honeybee Robotics.
Good morning, everyone. I'm very, very excited to be here. I was actually presenting at the last year's convention in Pasadena, and it looks like I've done a good enough job, so I was invited again. There are two things that get me out of bed every single morning, setting aside crying kids. The first one is touch life, and the second one is mind the sky. Under touch life, it's a quest for finding life in our solar system, and that's one of my interests. As you know, Mars is a primary target for finding life. Under Mind the Sky, it's in situ resource utilization. It's essentially mining local resources to sustain human presence and also robotic presence. And the Mind the Sky I was actually presenting last year, and today I'm going to talk about touch life or look for life. Let's go back. Let's step back and see how the space exploration actually happens. What's a natural state of space exploration? If you think about it, the easiest thing is to look through a telescope and see what's on another planet. But the information you're getting is very, very small because you can't really see that far. So if a technology is developed, you can send a spacecraft that will fly by or orbit another planetary body. But again, information you get is only limited to a surface and in some cases subsurface, but it's all non-contact. So if you put more money, develop further technology, you can actually put a lander on the surface to grant truth orbital informations. And also, this will just give you a one-dimensional data point. Imagine landing here on Earth in Sahara Desert versus Atacama versus Amazon. The information you're going to get are totally different. So this is just a single data point. To really explore, you have to go into the that's why we have rovers driving around for the past 20 years on the surface of Mars, and those give you a two-dimensional exploration. But it doesn't stop there. We all know that there is significant radiation and oxidation on the surface of Mars. So if you really want to find life, you have to go below the ground. And going below the ground is not just three-dimensional exploration, it's 4D. Going back below the surface means you go back in time. If you go to Antarctica and you get the ice core all the way down to 3 or 4 kilometers, you go back in the history of this planet million years. So that's why we know what was the climate 100 years ago, or 500 years ago, 1,000 years ago, thanks to these ice cores. So going below the surface is going back in time, and also another way to find life. So how would you do that? We've done some drilling or going below the surface of Mars, but the history is very short. We haven't done a lot, and it's very shallow. We haven't done very deep. The first sort of device that cut into Martian rocks was rock abrasion tool. It's a grinder that was sitting at the end of a robotic arm on the Mars exploration rovers, and the red was actually developed by our company and operated by our company for over a decade. This tool essentially helped uncover history of liquid water on the surface of Mars. On one of the first sols, what we found is this sort of striations right over here that could be biotic or abiotic. So this wasn't really released because the 50% of scientists thought, well, this could be live, and 50% thought, well, it could be in abiotic origin. So this wasn't really published, but these sort of surprises, await us, not just, on the surface, but few millimeters below the surface. Rock abrasion tool essentially showed us that rocks on Mars are very similar to rocks on Earth from a strength standpoint, and also that you can actually cut through those. We can develop technologies that can cut and go below the ground. The next mission was very, very fascinating. It's Mars Phoenix. Mars Phoenix had a scoop to pick up some Martian dirt, but underneath the scoop it had a drill. This drill was called RASP, and the purpose of this RASP was to cut through icy soil and icy ground and capture some of these ice particles. So this device was the first man-made piece of hardware that ever touched Martian ice. Decades ago, we were thinking there is ice on Mars, and in 2008, we touched ice. And we found that, and this device actually was also built by a company, so another great experience. What we found is that there is ice near subsurface. If you uncover a few inches of a top regolith, you get straight into ice. So you can bring a broom, sweep it away, and you can have an ice hockey game right there in the North Pole. It's right there. It's right there. But it's also a perchlorate. Perchlorate is a salt. Those of you who live on the East Coast know that in winter you put salt to depress freezing point. And the perchlorate does exactly the same thing. In fact, if you put enough concentration of the salt, you could have a liquid water at -70 centigrade. So you don't have to wait till 0 C. You can have actually liquid water flowing on the surface of Mars at -70 centigrade if it's hypersaline. So things are getting more interesting. And a recent addition is a Curiosity rover with its drilling system. The drill can penetrate approximately 2 inches or 5 centimeters into the rock and captures material for analysis. Curiosity have shown that weathering rind is actually relatively shallow, a few millimeters, so you don't have to cut through a lot of rock to get into unaltered rocks. It also showed that you can capture material, process it, and analyze it in situ. So this was a great, great demonstration. The rover is still going strong and is still exploring, and new data is flowing in pretty much every single day. And next is a Mars sample return mission. This is a rover that will fly next year in July of 2020. Its purpose is to capture these rock samples, those the size of a pencil, they centimeter in diameter approximately, and 5 centimeters long or 2 inches in diameter. The purpose of those is to bring them back home. We're not going to bring all of them. We're going to select which one to bring. But the future missions in the late 2020s and the early 2030s will bring the samples back and for analysis. And one thing about bringing samples back is you can analyze them for decades to come. The best science we've done on Apollo samples, the almost 1,000 pounds of rocks and soils that we brought from the moon, wasn't done in the 70s. It's being done right now because instruments that we have right now are way more sophisticated than the instruments we had in the 70s. So once you have samples from another planet, you can continue analyzing them pretty much forever. European mission has a rover called ExoMars, equipped with 2-meter drilling system. This rover, again, will fly next year, so Mars is going to be extremely busy. We heard that there is going to be a Chinese mission going to Mars next year. The Mars 2020 mission will go to Mars, and the ExoMars. And the purpose of this mission is to go up to 2 meters below the ground, capture samples, and analyze them by a suite of instruments. So it's going to be very, very exciting times in 2021. But what this also shows you is that we barely scratched the surface. So far, the deepest we went into rocks was probably a couple of inches, 2 inches at most, 50 millimeters. It's not very deep. to really find life, we have to go orders of magnitude deeper. So how deep do we need to go? Just recently, a Mars Express, Mars's instrument, found subglacial lakes in the South Pole. These lakes, right over here in the South Pole, they're approximately a mile deep and they're hypersaline. So they could be potentially a good location to drill to and look for life, because life requires liquid water, life requires energy, and life requires nutrients or organics and chemistry. And probably all of those ingredients are sitting there a mile below the ground. So what we need to do is develop a big drill to go to the South Pole and actually poke it and find life and prove that there is life in the solar system. These sort of lakes are not only on Mars. There's plenty of them here on Earth as well. Antarctica has a lot of lakes. One of them is called Lake Vostok. This is the deepest subglacial lake, 4 kilometers deep. I'll talk about it more. We also have lakes on the Devon Island in the Arctic. They're relatively shallow, 500 to 700 meters below the ice cap. And these are also hypersaline, just like on Mars, approximately minus 10 degrees centigrade. So when we drill down, and there is another group of folks looking at what would it take to drill down these 500 meters and get into these hypersaline lakes as a precursor for Mars mission. But you know, it's not 0 C, it's minus 10 C. So things are becoming more interesting. And obviously, Greenland, I was in Greenland last June, July. There is more and more lakes as the climate changes. Actually, this entire ice sheet starts floating on the water, and pretty soon it could actually slide down. That's a real problem. But every year we're discovering more subglacial lakes in Greenland. So what we have here on Earth is very similar to what we're finding on Mars. So Mars is becoming, again, more interesting, more Earth-like. So how have we been doing here on Earth in terms of drilling? The deepest hole ever drilled on this planet is in the Kola Peninsula. Kola is this tail of a Norwegian dock right over here. It belongs to Russia. They drill, the hole is called Kola because it's the Kola Peninsula. They drilled 12 kilometers deep. 12 kilometers deep. It took 20 years to do this. So it's not something that you can do overnight. But we've done it successfully. There were a bunch of technical problems, but at the end of the day, we reached 12 kilometers. And this is the hole itself. So it's not a museum up there. You can still find it. When it comes to ice, the deepest hole in ice is 4 kilometers below the ice cap in Antarctica. That's this Lake Vostok right over here. And this lake is under pressure. So when the Russian expedition actually cut through after 20 years of drilling, the water actually flowed into the borehole, and that's how they could capture this subglacial water without contaminating lake itself. So this is one way that could happen also on Mars. As we cut through into the lakes, we may find that the water is pressurized. It's going to flow into the borehole, and you can capture this, and you do not have to contaminate the lake itself. And if you look at the drilling depth versus mass, I put together couple of these graphs. This is log scale. So this is maximum depth as a system mass. So you have a couple of these data points depending on the type of a drilling system we're using, whether it's geotechnical, oil and gas, ice drills. To get down to around a mile, you're talking about 10-ton systems. So that's pretty heavy. If you do the same graph, but instead of mass, you have power, to get down to a mile, you're talking about tens of kilowatts of power. So just by taking terrestrial know-how and putting it on Mars is not going to cut it. We can't put 10-ton drill with 10 kilowatts of 100 kilowatts of power. It's not going to cut it. We have to be smart about it. So we went back to the drawing board, and we looked at all the drilling options. In a nutshell, you can divide them into three. The first one is mechanical. So this is what ice augers do for fishermen and things like that. Then you have the thermal. So here you melt ice, and that's how you penetrate just through heat. And somewhere between is a hybrid system. So what I decided to do is dig deeper into mechanical, thermal, and this hybrid system, and tell you pros and cons of each one of those. Melt probes, they're relatively simple. What you have is a hot point. So this tip heats up. Inside this sort of cylinder behind the hot point, what you have is a wire coiled up. So as you melt through, you're creating a melting cavity that refreezes behind a melt probe and traps this wire that carries the power to the surface. So this system goes one way. This means the instruments in a melt probe has to be integrated with the system itself. And this is an example of the ice diver developed at the University of Washington. In a nutshell, you have two ways to do melt probes. The first one is this sort of melt probe with a hot point right over here. This one shows a hot point with a couple of heaters on the side, so you don't have to melt entire cavity. You can melt sequentially less as the water moves to the top. You can have these melt probes essentially fully integrated. So you have RTGs or nuclear power inside the probe, and communication is done through some kind of RF transceivers that you leave behind as you penetrate down. And these kind of things we're looking at right now. Another option is what Ice Diver did, is put a wire inside, so this wire would come out and refreeze in a borehole, and this wire would provide power and a communication. If you look at the power versus penetration rate for these melt probes, you'll very quickly find that you're talking about kilowatts or tens of kilowatts to melt through. One of the first melt probes developed by Amott, featured right over here, was just shy of 4 inches in diameter and 2.5 meters long, and required almost 4 kilowatts of power in a warm ice. So if you go to Mars and cryogenic ice, you would need tens of kilowatts of power. So we know melt probes probably not going to cut it. So let's look at the electromechanical systems. These are wireline systems. They have a drill bit at the end. They suspend it on a wire, so that you don't have to bring this entire drill pipe with you. To go deeper, you unspool more of this wire. But as you go deeper, you capture the sample, sort of like this, and when you pull out back to the surface, you dump the sample, you go back into the same hole to capture another sample. This is how actually all the drilling, or most of the drilling, is done in Antarctica. This system weighs maybe 100 kilograms, and you can drill 20 meters a day. It's mostly manual. So within 2 years or 100 days, this is 2 years that took in Antarctica, but 100 days altogether, you can get down a mile deep. So something like this could potentially work. That's what we did. We took this system and we turned it into a fully robotic drill. It stands at just over 4 meters long. It has a bunch of instrumentations, bunch of actuators, motors, computers inside it. There is a wire right over here going to the spool, and right on top is the most exciting thing. It's Watson. Watson is a deep UV Raman spectrometer, which looks for organic material. So as you go down, it can look at the borehole and see if there is actually some organics in the borehole without even having to take material to the surface. We took it to Greenland. So this is our Watson drill. We had to put this tent behind it. Fortunately, there was no wind as we were putting, otherwise this tent would fly away. We put it down. This is the tent with the drill sticking above. If you go inside it, this is what you would see. We had to dig out this cold pit. This is where we would store ice cores, and computers right over here to run the drilling system. And this is what we see when we look at the ice. These are the hot spots that are reminiscent of the a bioburden or microbial communities. We hit over 100 meters, so we are super excited. We took one of these ice cores, we melted it. We didn't tell scientists we did that. And so it was good scotch with 500-year-old ice. It was a lot of fun. So let's look at a hybrid system. Hybrid combines the best of two worlds, mechanical and a heat probe. It sits on a lander right over here, and it consists of two main systems. The bottom one is a hot one. This is where we have nuclear reactor. This is where you generate a lot of heat. This is where you generate a lot of power. And above this, we call it a cold area. This is where you have batteries, instruments, computers, and also these communication tethers. So we pull it out. This tiny line that you see, is essentially fiber optic because all the power is generated by Stirling engines and nuclear reactor. We've done a lot of testing in a lab to figure out how much we're saving by doing this so-called slushing. So it's not really mechanical drilling, it's not melting, it's somewhere between. If you ever drank slush, it has a lot of ice in it, but it's also fluid. So we thought that by not melting all the ice, you could actually save a lot of energy. And what we found is that indeed slushing gives us order of magnitude better penetration rates and less power or energy as opposed to the melting. It's not as good as mechanical drilling, but mechanical drilling has problems of moving chips to the surface.
The Earth is the only world known so far to harbor life. There is nowhere else.
So we are actually building this thing right now, minus nuclear reactor, obviously. But probably sometime next year, we're going to be running end-to-end tests in a big freezers and hopefully go to England, to Greenland to deploy it and to show that actually penetrating down hundreds of meters below the surface is actually doable. So with this, I'll conclude that in three main bullet points. We can easily penetrate a mile deep here on Earth, and we just have to put a bit more effort into developing technology that can do this thing on Mars. But I can, in my lifetime, I think we can totally do this. And the hybrid system is definitely a way to go. SLUSH is probably, at least in my opinion, I'm kind of biased to this, is a way to go. So with this, I'd like to thank you and open for questions. Yeah, so there's a concern that melting is going to potentially destroy the biota or microbial activities. Yes, it's true, but if you think about it, the microbes actually, or microbial communities, do need liquid to actually reproduce. So if they're sitting in ice, they're dormant. They're not going to reproduce. Also, the system, the purpose is really to get down to the ocean. It's not we will analyze meltwaters as we penetrate down, but we are most interested in getting down to the ocean and capturing some of this liquid and analyze it.
Could you comment on a future Europa lander mission how could your technology be adapted to drill through the much thicker ice cap on Europa, and what kind of mass might that require to be able to get to the liquid water layer?
Yeah, it's actually a very good question. The video that you show actually was for Europa, and 15 kilometers deep ice sheet. Fundamentally, Mars is easier because you have stable ice body, and it's relatively shallow. Europa is extremely hard because you have radiation. You have tides that continuously shift ice back and forth, and you have a lot of, I call it geological uncertainty. We don't know whether we're going to have these lenses, or subglacial lakes before we hit the ocean. So it's much harder, but fundamentally the approach of hybrid system and using tether or fiber optic for data transfer is a way to go. So the approach would be the same. We would just have to it's going to take more time to do this on Europa, and autonomy would have to be significantly better. Yes, we can. So the Watson drill was an example of this, where you bring the instrument to the sample as opposed to bring sample to the instrument. So you can pack a lot of instrumentations and the sensors in your probe. So as the material passes through by the drill, you can sample some of this if it's solid, or you can suction some of the liquid and analyze it. Yeah. Yeah. Yes. So what makes the probe going down? So it's gravity. And what happens when you hit a rock or things like this? And I'm glad you asked this question, because that's a reason why we kind of stay away from melt probes. If it's a melt probe, it's going to get stuck. You can't really melt rock. And if it's a big rock, it's going to definitely get stuck. If it's a tiny rock, it's going to essentially potentially float underneath the melt probe continuously in your pool. Mechanical drilling system can actually cut through this, and then cuttings can be mixed with water and moved up.
Thank you.
Thanks, Bob.